So I haven't answered any questions in my open math. I haven't even looked at any in my open math today. But we can answer questions now if you have any. About chapter 11. Does anybody have any chapter 11 questions?
Number 14.
14. Same volume with different masses. Okay, so so this one has to do with the definition of the buoyant force. What is the definition of the buoyant force? That would be under Archimedes' principle. Net upward force on any object in fluid. What does it say right there? What is the buoyant force equal to? The weight of the fluid, what? Displaced. So if you have some fluid in here and you put some object into it, how do you know how much fluid is displaced by that object? The object has some volume because it's a three-dimensional object. So if it has a volume of V, how much fluid will be displaced? Volume V, right? Because the thing that's displacing it is the object. So if an object has a mass of M and a volume of V, so the buoyant force is directly proportional to the weight of the fluid displaced, and it's actually equal to it, equal to the weight of the fluid displaced. The weight of the fluid is going to be equal to the volume of the fluid displaced times the density of the fluid displaced. That'll be the volume times the density will give you the mass, and then you have to multiply by G. G is the same for everybody if we're using the same fluid every time. This is the same for everything. The thing that changes is volume. So that means the buoyant force is directly proportional to the volume of the fluid displaced. So if you have a mass that has its weight pulling down on it, doesn't even matter that weight. But if you have a mass that has this volume, and then you have the same mass, has the same amount of mass, but it has a much bigger volume, what's going to be the relationship between this buoyant force and this buoyant force? Buoyant force 1, buoyant force 2, greater than, less than, or equal to, right here. Which one's going to have the greater force on it? Why? Why? This says that the buoyant force is directly proportional to the volume of the fluid displaced. So this is like a chunk of steel that's solid. This is like a hollow box of steel. Which one is going to have more force pushing it upward? A hollow box of steel is like a boat. Right? Which one has more force pushing it towards the top? Yeah, the boat, right? A boat has so much force pushing it to the top that it floats on the top. This one sinks to the bottom. Same mass, and because it's directly proportional to the fluid displaced. It's like you drop a billiard ball in your pool and it sinks to the bottom. That probably floats, You drop a ball of hard rubber to the bottom, it's just solid hard rubber, it just sinks to the bottom. But if you blow that hard rubber ball up into a big balloon, it floats on the top, right? Because you filled it with air, you've decreased its density. By spreading its mass over a great big volume, you've decreased its density. So this one has a higher buoyant force, which is why it floats. The buoyant force is directly related to the volume. So you have a small volume, you have a small force pushing it up. If you have a big volume, it's a big force pushing it up. So now, can you answer this question? We have 3 cubes that have the same volume but different masses. Does the mass of the cube matter? Does the buoyant force have mass inherent? No, it has volume of fluid displaced, density of the fluid displaced, and the gravitational constant. So it doesn't care about the mass of the cube. It just cares about the mass of the water displaced times g. So that's not going to change anything. In the second test, the 3 cubes have the same buoyant force. In the second test, the 3 cubes have the same mass, but different volume. So that's this one. Same mass, different volume. Which test will the 3 cubes have the same buoyant force? Which test is the buoyant force not going to change? Buoyant force depends on volume, right? So which one of these is not going to change because of their volume? Which one of these tests? The first one. The first one has 3 separate masses, different mass, like 3 different pieces of material. One's made of plastic, one's made of steel, and one's made of neutrons. If you had a block made of neutrons, you'd be in trouble. But it's cool to think about. Like a block of neutrons the size of your fist would have so much gravity that we would all get sucked into it and be plastered to the surface of it. Cool, huh? Anyway. Point is that you have these 3 different masses, but they're all the same volume. When you put them under water, they displace the same volume of water, and water all has the same density, so it has the same buoyant force on each. They won't all react to that the same because they have different weights, but they will still have the same buoyant force. And why? I'll let you figure that out. Any other questions from chapter 11?
Yeah, 16. I think it kind of goes with that.
I love that. Man, I forgot to eat lunch, and I am feeling it. I'm hungry. It's Taco Tuesday. Can I eat tacos? I love tacos. You ever had pupusas? Okay, so imagine a soft taco made with instead of like a hard corn tortilla, it's made with soft corn tortillas with cheese. So it's like a quesadilla. But sometimes they put meat in it too, or even vegetables in there too. It can be all kinds of things. So it's like a quesadilla for your shelf. And then it's got like pickled, spicy salad inside. Phenomenal. It's like pickled cabbage and carrots and onions and tomatoes with this really nice spicy salsa that's made from tomatoes and chilies and garlic. It's from El Salvador. Like if you're ever near an El Salvadoran restaurant, get some pupusas. They're so awesome. It's like one of my favorite foods on the planet. Anyway, I have some Salvadoran friends that need to go over and eat dinner at their house. All right, so anyway, we have 120 Newton block. So that's the weight. 120 newtons is the weight, right? And it displaces 600 newtons of water. Right? So this is like, that's the weight of the water. So this is a kind of a trick question. If you understand the buoyant force, it's really easy. Buoyant force equals the weight of the fluid displaced. What did they just tell you? It displaces 600 newtons of water. Newtons. 600 newtons is the buoyant force.
So when it's not at equilibrium, does that change? So like if
Nope.
17
At the buoyant force, oh, so, okay, so the buoyant force will change if the block is floating above the water. Because if the block is floating above the water, not all of the block is displacing water, right? So only a fraction of it will be displacing water. So if it's a 600 Newton buoyant force in a 120 Newton block, that means that the buoyant force is much bigger than the weight. That means that it's going to bob along on the top. So only a fraction of it will actually be under the water. But we have an equation for that fraction thing, right? There's an equation that tells us about the fraction of a block submerged if you know these things. So if you can take these things and plug them into the fraction equation, which is also in the Archimedes chapter, then you can calculate the second one. But it will definitely float at the surface. Now if this number and this number are equal, then it will float underwater and be at equilibrium. So if it's at equilibrium because they're equal, then it floats underwater, and the fraction will be 100% of it will be underwater.
So, I mean, from the book, I looked at the equation, but I don't really know what it wants me to put in the equation. Is it just...
Which equation? The fraction submerged equation? Okay, so in the fraction submerged equation, if we go down here, right here, you have you have a couple of different equations you can use. You can use this one, which is the density of the object over the density of the fluid equation, right? You could use that one. But there's also right here. There's also the volume submerged over the volume of the object equation. But then there's also the mass of the fluid over density of fluid over mass. So essentially, you can use any of these equations. And in the end, because it says density equals mass over volume, and the mass in, let's see. So yeah, so you have the mass of the fluid, and you have the mass of the object in your problem because you have the weight, right? If you have the weight, you can replace, instead of mass, you can plug in the weight because they're both multiplied by g, right? Or you can just solve for the mass and plug in the mass. And then you can, let's see. Let's see if you're, can't remember what they do here. 120 Newton. Oh, so this one takes a little bit of trickery. Because you know that it's displaced 600 newtons of water, you actually know the volume of the block by calculate the volume for 600 newtons of water by using the density of water. Then you can calculate the volume of the block and the volume of the water. Let's see, density of the block, density of water, density of the water equal the mass of the water over the volume of the water. And you're trying to solve for this because you know the density of water. The density of water is 1,000 kilograms per meter cubed. And we know the mass of the water is 600 newtons. 600 newtons divided by g is the mass of the water. And then we can calculate the volume of the water. And then, once you've calculated the volume of the water, displacement is completely underwater, that is equal to the volume of the block. And then you can use the same equation to calculate the density of the block, and then you can use this equation. Does that make any sense?
Yeah, I think you know the 1,000 kilograms of water.
That's for water. So the density of water is 1,000 kilograms per meter.
Oh, okay.
Any more questions? I had a lot of yawning today because I'm hungry. I'm hungry, I get tired. My niece is coming today. I have a 5-year-old niece who's like super cute. She's super funny. And it's just kind of fun to have little kids around the house. I mean, not have like teenagers and teenagers are obnoxious. So I get a little change today. My 5-year-old niece coming. All right. And 2 nephews as well. But she's the cutest one. All right. Any more? You good? All right. So now let's go on to chapter 12. Was I right? Is chapter 11 easier than we've been doing so far? Yeah. Good. Chapter 11 is a kind of a break. We're on the downhill now. We get to cruise to the end of the semester, which is nice. Fluid dynamics. So chapter 12 is about how do you fly an airplane. Biological and medical applications. That's not fun. We want to fly an airplane. It's also how fire hoses work and lots of other things. But fluid dynamics is a very interesting topic. And it has to do with when fluids start to move. And we're going to start off with fluids moving through like pipes, because that's simple. When you have a certain amount of fluid, it could be water, oil, air, whatever, moving through a pipe, a cylinder like this, we could talk about the velocity of the fluid, and that can be useful, especially later on. But even more useful for now is this flow, which means how much volume is moving per second. Because velocity is how much distance per second. We want to know how much volume is, like how many gallons per second, instead of how many meters per second, right? So we take this, the definition of flow, which is going to be Q, because we've already used F. We try to use the whole alphabet. But we have Q equals the volume over time. So that could be in gallons per minute, or it could be liters per second. It could be cubic meters per fortnight, whatever, right? And we're going to use this velocity to figure it out. So if we have a pipe that has this radius R, which creates this cross-sectional area A here, and in the time of, like, say, 1 second or something, this area, this part of the fluid moves from here to here, this distance d, then this pink thing is a volume. It's a cylindrical volume. It's like a little can of water in our pipe, right? It's a little piece of water, and the volume of that is equal to A, the area right here, this little circle, times d, which is the height or the length of this can. A times d is the volume. So instead of volume, we have A times d. Q is equal to A times d over time. Well, distance over time is velocity. So we can replace the distance divided by time times the average speed or velocity of the fluid through the tube. So now we have a very simple way to calculate the flow. It's the cross-sectional area of the tube times the speed of the fluid through the tube. And you're done. Right? So your heart will pump 5 liters per minute. So that's the flow. 5 liters per minute is the Q. And we want to know how many liters, or how many meters cubed actually, it's going to pump in a lifetime, 75 years, at 5 liters per minute. So we put in the 5 liters per minute for Q, and we put the 75 years in for time after we've solved this equation for volume. Q equals V over T, so V equals Q times T, right? So we have our Q, which is the 5 liters per minute in the 75 years. We convert the liters into meters cubed. There's 1,000 liters in 1 cubic meter. And in case you're not seeing that, You imagine a liter is 10 centimeters on each side, about this big. Excuse me. It's about this big. So a meter cubed is 10 of those on each side because it's 100 centimeters on each side, right? That's a meter cubed. So it's 10 liters times 10 liters, that's 100 liters, times 10 liters up, that's 1,000 liters. So there's 1,000 liters in 1 meter cubed. So there's the conversion right there for liters to cubic meters. And then converting years to seconds, no, not converting years to seconds, minutes, there we go, minutes, because we have minutes. We have minutes right here, and we have years right here, so we're going to convert years to minutes. It turns out there's 5.26 minutes per year. 5.26 times 10 to the fifth. Doing that 60 times 60, no, 60 times 24 times 365. Anyway, that gives us 2.0 times 10 to the fifth meters cubed. That's a lot. 20,000 tons of blood. Right? The pool at Cody Park holds about 1,000 tons of blood, 1,000 tons of water. Probably a little bit less because it's a very shallow pool for a lap pool. Most 50-meter lap pools are at least 8 feet deep and usually 12 or 10 feet deep. So anyway, there is our flow equation. The flow is the cross-sectional area times the average velocity. And it's kind of interesting because the flow in a closed tube, it has to obey this kind of rule. I can't remember whose rule this is, or law, it's Roussel or somebody. But anyway, no, I think it's, anyway, I don't remember. But it's called the continuity. It's called continuity. And imagine it's like a freeway. Okay, you have a freeway that starts off it starts off 4 lanes wide, then it goes down to 2 lanes wide, right? But you're trying to get the same amount of cars down the freeway in the 2-lane part as you are on the 4-lane part, right? What are you going to have to do? Normally on a freeway, what happens when you go from 4 lanes to 2 lanes? What happens to the traffic usually? If you have a lot of traffic on the highway, say you're going 60 miles an hour, and suddenly you come to 2 lanes, what happens to the speed of the cars? It usually slows down, right? And so what happens is in the 2-lane part, you don't get as many cars through as you did in the 4-lane part. What happens is it backs up, right? So it slows down. However, if you got to the 2-lane part and you sped all the cars up, made them go faster, you could actually get the same amount of cars through in the 2-lane as you did in the 4-lane. In the 4-lane, you could have 4 cars, driving side by side at 60 miles an hour. But in the 2-lane, if you want 2 cars to go side by side, they're going to have to go twice as fast, 120 miles per hour, to keep the same number of cars going through if they're going to drive side by side and get the same number of cars through every minute. So in fluids, this actually does work out fairly well. Because in fluids, there's not like a speed limit, right? There's not people flying around and sitting in the fluid trying to survive. So what happens is that if you have what we call laminar flow, which is very clean flow. Laminar flow looks like this. You have your wide pipe, and then you have your skinny pipe. And the flow, if you put in like little streamers into the flow, if you put in little like drops of food coloring, or what we would call bromo blue, it's a very strong coloring, then the coloring would travel through here like this, and you would see it travel in these lines, and they're laminates essentially. Think of them. And each line would have this smooth travel through here. It's not what really happens in real life, but this is the ideal. This is what you're really looking for. So cars are often put in wind tunnels and tested for laminar flow. You can see they've got these little smoke starters, smoke things here, and you can see that the laminar flow is pretty good around the cars. Especially sports cars, the laminar flow is very good. You can even see that the laminar flow is going through the car and under the car. They're testing for that as well. Sports cars have very good laminar flow around them, which is what you want. There's a couple of places in a car where you prefer to have less laminar flow, and that's usually along the back of the car is where you want less laminar flow, because that's going to produce a little bit of force downward on the back wheels, which is good because it keeps the car on the pavement. Some cars have a lot of non-laminar flow along that back edge, which is not great, but it's not terrible either. You'd much prefer to have more laminar flow coming off the end than that car, and less of this. This is called turbulent flow. You know, if you have a convertible, it's just inevitable you're going to have turbulent flow right there. And in this one, you have Ferrari even has laminar flow through the car. That's pretty cool, I think. But then you have cars like, see, like this one, you can see there's a little bit of turbulent flow right here, right where this little wing is, and that's the whole purpose for that wing. That whole purpose of that wing is to have force downward here, and that turbulent flow is an indicator of that force. And you can see the laminar flow under the car is actually really important. If you have turbulence under the car, the car will lift off the ground, and that's really bad for fast cars. It's bad for any car, really. So this is what we call laminar flow. I mean, look at the laminar flow on a Formula One car. That's not even real. That's a picture. That's a drawing. But Formula One cars do have excellent laminar flow. They do it for cyclists. They do it for airplanes. All this kind of testing. I really want to see well, here's a really bad one. This is like the, I don't know what this is, like one of the cube car or whatever it's called. See, it's got this turbulence right here, turbulence right here, and turbulence right here at the front bumper. All kinds of forces acting on that car in goofy ways. Here's an electric car designed for high efficiency, extremely laminar flow, right? And all these things have a reason. Here's my car when I was a kid. It's a toy, but I still have one of these. I had a real one. Lots of turbulent flow behind the car, not very aerodynamic. The front of it is surprisingly aerodynamic, but the back not so much. The Mini, terrible, right? 1960s race car. Love them. Anyway, this is what you can do if you're in the wind tunnel. So anyway, these cars undergo these tests for laminar flow, and if you have laminar flow, you get these very let's see, go back to you get these very nice lines here without turbulent flow. What really happens is the water comes in here, or the fluid comes in here, and it hits this wall and it bounces off and bounces back, and you get these little eddies, and you get turbulence in here, and that might even cause some turbulence here, and that creates essentially friction, and this slows things down, kind of like on a real highway like we were talking about before. And so what you do in pipes when you go from big to small is you make it so that there's nothing to run into, so you have this nice even, slow, smooth transition for this laminar flow to go into, right? And this is actually what we call a nozzle, like nozzles for sprinklers, nozzles for the nozzle for for a fire hose. Jet engine nozzles are made this way. Rocket nozzles are made this way. Try it. Sometimes you actually want to create the turbulence. Sometimes you don't. In sprinkler nozzles, they actually want to create the turbulence because they want to create a spray in the sprinkler. And if you just want the water to go a long ways, then you want this. You want this to happen, because what happens here is when you get into this part, because the area is so much smaller, the velocity gets really, really big. And over here, the area is really big and the velocity is really small. And what's equal here is the flow. If the flow rate, because we have this laminar flow, if the flow rate is the same, then you get big velocities in small pipes and small velocities when the pipe is big, when you have one flow going from one to the next. Right? Big velocity with the small pipe, small velocity with the big pipe. Same as a river, right? Where do the rapids occur in a river? In a river, the rapids occur when the river gets small. And it's usually much smaller when it's steeper as well. So you also get steep, right? But when the river slows down, it widens out and everything slows down. Everything's wide and easy and slow. No waves or rapids. When it gets narrow, that's when you get the rapids, because they're moving faster. So we call this the continuity equation. Continuity means that the flow is continuous, right? And it means that the flow at one point in the pipe is equal to a flow at the second point in the pipe if you have laminar flow. And this also only works if the fluid is not compressible. So this doesn't work for most gases. Gases are easily compressible. It works okay for most gases as long as the pipes are pretty big and the change isn't extreme. But it won't work really well in all cases. And it works well for most liquids. Most liquids are very difficult to compress. Some liquids are easier to compress than others, but most of them are pretty difficult to compress. So it works truly quite well for most liquids. The flow at one point is equal to the flow at the other point, which means the area times the velocity at one point is equal to the area times the velocity at another point. And here they show a nice little graphic of that. The flow is represented by an amount or a volume of fluid passing by a particular point every second. Well, this volume passing by this point in 1 second is the same as this volume passing by this point in 1 second. But notice how much distance this volume has to move in 1 second compared to this one. So this one has to move much faster to get through that longer distance. So let's use the continuity equation. We have a nozzle on a garden hose. The nozzle has a radius of 0.25 centimeters. The garden hose a radius of 9.9 centimeters. The flow rate is 0.5 liters per second. The speed of the water in the hose and the nozzle is what we're going to calculate. So the velocity at the hose is going to be equal to the flow rate, which is 0.5 liters per second, and they make the conversion into cubic meters, divided by the area, which is pi times the radius squared. And they do the pi, and they just plug that in right there. So the velocity in the hose is 1.96 meters per second. In the nozzle, we use the area of the nozzle, cross-sectional area of the nozzle, and the same thing. Or in fact, actually, they go back to the flow rate equation and calculate it from there. But you can also just do it from the area and from the area and the flow rate, either way. But they do that, and they get 25.5 meters per second. 1.96 in the hose, 25.5 at the nozzle. And that's what nozzles are designed to do. Nozzles are designed to speed up the fluid. And if it's a garden hose, that makes the water spray further out of the hose because it's coming out of the hose very fast. It travels farther before it falls and hits the ground, which is ideal. That's particularly ideal for firemen. You know, firefighters use a hose that's usually 2, 3, maybe even 4 sometimes inches in diameter. So it can be as big as like this, and maybe as small as this. So pretty big hoses, and they also have very high speed water in the hose. The pressure is extremely, well, they call it high pressure, but it's actually low pressure. But the point is that there's lots and lots of water going through. The flow rate is extremely high velocity hose. And then as it hits the nozzle, it goes from that 2, 3, 4 inches all the way down to very, very small and adjustable as well. They can adjust that size. And so it can go up to extremely high speeds. And that gives them the advantage of fighting a fire from a distance. So if it's a high building, they can shoot the water a very high distance. Or if it's just too hot of a building, they can shoot it from a far long distance and hit the building without endangering their own lives. And they can deliver a lot of water quickly. So this is actually pretty interesting. The blood flow in your body, you have your veins and your arteries. Your main veins and arteries are quite big, like centimeters kind of big. So the aorta, which is one of the biggest, has a 1 centimeter radius or a 10 millimeter radius. And you have a blood flow at 5 liters per minute. So that's your Q right there, 5 liters per minute. And this is your radius for your aorta. But the blood is also flowing through the capillaries. Now the capillaries are the tiniest little blood vessels in your body that are out in your muscles and surrounding your cells and things like this. And those are super tiny. The rate of blood flow in the aorta is 5 liters per minute. The speed of the blood in the capillaries is 0.33 millimeters per second. So they're telling us the blood flow in the aorta and the speed in the capillaries. So we're going to use the continuity equation, which has both of those things involved, to calculate the velocity of the blood in the aorta. So Q equals A times V, or A1 times V1 equals A2 times V2, or whatever else. And then they're essentially going to solve this because the flow rate is the same. All they have to do is solve this equation for the velocity in the aorta using the flow rate in the aorta and the radius in the aorta. 0.27 meters per second gives you the velocity of the blood in the aorta. Then they're going to calculate how many of these capillaries they must have in order for this to be true. So this is where they use where they're going to use the the continuity equation, but they modify it a little bit. When you go from one pipe into multiple pipes, you have to multiply by the number of pipes on each side of the equation. So for the aorta side of the equation, we have one aorta, so N1 equals 1. But on the capillary side, we have many of those, so N2 is going to equal whatever it's going to equal. And we solve for N2 in this equation. So N2 equals N1 times the area of the aorta times the speed of the blood in the aorta divided by the area of the capillary and the speed of the blood in the capillary. And when we solve for that, it turns out that we have 5 billion capillaries in our body. So 5 billion capillaries. It's kind of insane. Notice that this is not a huge change. It goes from 0.27 meters per second to 0.33 millimeters per second, which is a change of about 1,000. But we have 1 billion of those capillaries, right? So that accounts for that change not being as big as it might be. So that's flow rate and the continuity equation. Well, it turns out that there's energy in fluid, in flowing fluid, in just sitting static fluids, fluids that are just sitting around. Fluids can be like any other object. You can lift them high up in gravity and give them potential energy, and when they fall down a hill, they gain kinetic energy. So fluids can have kinetic energy and potential energy, but they can also have energy associated with their pressure. So pressure is kind of a form of potential energy, in other words, and other things. So remember we had this equation for conservation of energy. We're going to have another equation called Bernoulli's equation. This guy right here. And it's going to be an equation associated with energy. Now, here is Bernoulli's equation. Pressure plus 1/2 rho v squared. What does that look like? Well, that looks like 1/2 mv squared. And it is related to kinetic energy. It is not exactly the kinetic energy. It's missing something. It's actually missing the volume of the fluid that's moving. But that's actually more convenient here. Then we have a rho gh, which is a lot like, well, it doesn't even say that here. Rho gh, which is a lot like potential energy. In fact, it is related to the potential energy of the fluid. If the fluid goes from a height of h down to another height of h2 or h final or whatever, then that change in height is going to be, you're going to have to put that change in height into this equation to keep track of the energy in the system. And if you have a closed system where the fluid is flowing from one point to another and no fluid is lost, no fluid goes off somewhere and is lost, then this equation is very much like the conservation of energy equation where it's always constant. So you can have the pressure plus 1/2 rho v squared plus rho gh, 1 equal the pressure 2 at a different place in the system, plus 1/2 rho v2 squared plus rho gh2, and that has to be equal. So you get this kind of conservation of energy thing. Well, the consequences of this are kind of interesting. So how many of you have been on the freeway and been going fairly slow and then had like a truck pass you going super fast? And you feel this kind of push, right? I have news for you. It's not actually a push. It's a push and a pull. What happens is as the truck comes up on you, it pushes you at first, but right when it's passing you, it's actually pulling you towards it. There's a pull towards the truck. And then as you go away, there's another push. So it's a push, pull, push. And that pull comes from this equation. That idea of this pull in between comes from this equation right here. It turns out. It's a Bernoulli effect. This is also true of boats and big ships, any kind of boats actually, or ships. So I once went on a trip, Boy Scouts, to Lake Powell. Lake Powell is a lake in Arizona and Utah, made by a big dam, and it's got all these canyons in it because it's in these canyon lands. Lots and lots of really tight canyons in it. It's well known for these canyons. And one of the dangerous things is when you're in one of these canyons, if it's a really tight one like this one, you can see is only a few boats wide, and you can get down to it where it's only one boat wide, or maybe 2 boats wide. If you get into those little canyons up there and another boat's coming the other way, you have to be extremely careful, because as you're going past each other, you can get this pulling force between the boats that can actually crash the boats together very easily. So you have to go very slow to minimize that force in between the boats. If you ever have a chance to go to Lake Powell, it's definitely worth the visit. There's so many cool things to see there. But anyway, this Bernoulli effect, as it is called, is the same effect that makes planes fly. And what does it come down to? It comes down to moving fluids. When moving fluids are moving through, around, or between things, it actually changes the pressure of the fluid on those objects. So as we're sitting here, not moving, we don't really feel any pressure effects. But if you're driving in a car, you definitely do. If you're driving in a car and you open the window and that fluid, that air is moving past you very quickly, you can feel that effect. And we perceive it as wind, but it's not wind at all. It's the fluid is moving relative to us. We're moving relative to it, however you want to think about it. And I don't know if you've ever noticed this, but if you have a little piece of paper on your dashboard and you're driving in your car, what happens to that piece of paper? Does it get blown into the car? No, it gets pulled out of the car. The pressure outside the car actually is lower than the pressure inside the car. So the air inside the car, the pressure inside the car blows the paper out. Great story about that, actually. I must have been 15 or 16. And my dad and I are driving home from church one day. My dad was a scientist. And he had this stack of papers he'd been working on. It was a report he'd been working on. It was like this tall. All these papers typed. And he had it sitting on his dashboard. And we're driving away from the church, and he takes a turn a little bit fast, and the entire stack goes out the window, and I'm sitting in the passenger seat. And it goes out my window, the entire stack. And they're not stapled together or anything. And in some freakish reaction, I swept my hand right across the top of the pages as they were going out the window, and I pinned them to the door and didn't lose a single sheet. It was like the most awesome, people are awesome moment ever. It was so cool. And we pulled over and I pulled every sheet back in. They weren't even hardly messed up. Just a few bottom sheets were out of order. Not out of order, but just a little bit, splayed out. But man, it was awesome. One of my best, awesome moments of my life. I've had a pretty boring life. But anyway, the point is that Bernoulli's law, right? This thing affects the pressure around objects. And how does it affect it? Well, we're going to learn about that. What happens if the fluid isn't moving at all, though? Bernoulli's equation has velocity in it. The velocity of the fluid right there, right? Velocity of the fluid in one part, velocity of the fluid in the second part. But what happens if the fluid isn't moving? What happens to Bernoulli's equation? Where Bernoulli's equation becomes essentially a pressure and a potential energy. So you have pressures and potential energy. We've actually seen this equation. This is actually the equation for the pressure of a depth of a fluid. We saw this in the last chapter. So Bernoulli's equation is an adaptation of the pressure equation from the previous chapter, adding on this moving fluid thing. So what happens if the fluid is moving but it doesn't change height? If it doesn't change height, then this H part of the equation goes away and you're just left with pressures and velocities. So let's look at that really quick. If you have a fluid that has a pressure at one point and a pressure at another point, and let's say that we know the pressure at point 1, but we don't P1, but we don't know pressure P2. But we do know that the velocity of the fluid increases. So the velocity here might be 1 meter per second, and the velocity here is 2 meters per second. What's going to happen to the pressure? Well, let's take a look at that. So what do we know? We're starting off with pressure 1. Let's say that pressure 1 equals 1, we'll say it's 1 Pascal. That's very low pressure. And we'll say that pressure 2 equals 2 Pascal. Just make it simple. No, we don't know what it is. This is the question mark. We're trying to figure out what pressure 2 is. Pressure 2 equals question mark. We're not sure. We know that velocity 1 of the fluid is going to be 1 meter per second. And we also know the velocity 2. We know that it speeds up to double, 2 meters per second. We want to know what pressure 2 is. Well, the equation says that pressure 1 plus rho 1 half rho V1 squared equals pressure 2 plus 1/2 rho V2 squared. Right? So pressure 1 is 1. 1/2. Let's say we're doing water, and so we'll use 1 for water, 1,000 or 1 or whatever. So rho is just going to be equal to 1. And then our V2 is 1 squared, so that's 1 times 1, 1/2. And then P2, we don't know, plus 1/2 times 1 times 2 squared. That's 4. Right? Oh, sorry, 2 squared, which becomes 4. So on this side of the equation, we have 1 plus 1/2, which is 1.5-ish, right? And on this side, we have pressure 2 plus 1/2 times 4, which is 2. That's probably not the best example because of this pressure over here. Let's say that, let's start with a pressure of 2 over here. So that we have 2.5. So we're starting with a pressure of 2, and we end up with 2.5 on this side, and over here we have a speed of 2 that gives us 2 plus our second pressure. So our second pressure has to be 0.5, right? For this to be equal, right? In other words, our pressure went down. Our pressure started at 2, and then we sped up the fluid, and the pressure went down to 0.5. Now, this is something that most people don't understand intuitively. Most people assume that if the fluid is going faster, the pressure is higher. For example, we call it a high-pressure nozzle on a hose when we put a nozzle on the hose that makes the water come out fast. But it's actually a low-pressure nozzle. A nozzle that makes the water come out faster is actually lowering the pressure of the fluid and increasing the speed of the fluid. Okay? So anytime the air goes from a big part of the pipe to a small part of the pipe, it's going to speed up, we already knew that, but it's also going to lower the pressure in the small part of the pipe. If you go from a big pipe to a small pipe, smaller pressure in the small pipe. Lower pressure, bigger pressure in the big pipe. Okay? I guarantee you, somebody's going to mess that up and go big pipe is big pipe is big pressure, small pipe is small pressure because you're thinking compression. This is true for the fluids that do not compress. Remember, we're in the non-compression. It's also true for fluids that are laminar flow. We don't have any compression. We don't have any turbulence. We have nice laminar flow. Fluids that don't have any friction with the tube that they're in or whatever. It's very ideal. But it works fairly well. It works fairly well for most gases as long as there aren't extreme changes to compress the gas, and it works fairly well for most liquids as well. However, you guys should know this because this also works just out in the air. What happens to the pressure when there's a storm coming? You've heard this on the weather before because we live in storm country. When the storm is coming, what does the weatherman say about the pressure? It's going down, right? If the barometer is falling, that means the pressure is going down. That means we're in trouble of having a storm. The pressure going down does two things to the atmosphere. It creates faster air, which we call wind, right? And that always happens before a storm. The air starts moving, and it actually creates lower energy for the water in the air. It lowers the temperature of the water in the air, and it lowers the energy of the water in the air so that that water in the air that is gas, it's a gas water, it's water gas, like steam, it turns into liquid, and it creates rain. Right? So pressure goes down, wind goes up, because when you have low pressure, you have high speeds. right, of fluids. And also you get rain. So here they're going to actually calculate the pressure when the speed changes, when the speed speeds up. So here, remember our equation looks like this. We have this big old equation for Bernoulli's equation. Pressure 1, velocity 1 squared, height 1, pressure 2, velocity 2 squared, height 2, all these, right? If we don't change height, then this part, and this part goes away. And that's going to happen in this example. So we're not going to change height, so we don't have any rho GH on either side. But we're going to solve this equation for pressure 1 if we know pressure 2. So they know pressure 2. Why do they know pressure 2? Let's see. We have water in a hose that's going from a speed of 1.96 to 25.5. That's from the previous example. So that's speed 1 or velocity 1. That's velocity 2. Then we want to calculate the pressure in the hose. The pressure at the nozzle is 1.01 times 10 to the fifth. Why? Because they let it out of the hose. Once you let the water out of the hose, then the pressure on that water is just atmospheric pressure, which is 1.01 times 10 to the fifth newtons per meter squared. So that is the pressure 2. They plug that in for pressure 2, and then they solve this for pressure 1. And it looks like this. Pressure 1 equals pressure 2 plus 1/2 rho v squared 2 minus 1/2 rho v1 squared. So when they plug everything into that, they get this for pressure 1, 4.24 times 10 to the fifth. That's 4 times as much pressure as the pressure of the water outside the hose. So the spraying water that's spraying super fast is at lower pressure than the pressure inside the hose. And it should actually be a little bit obvious. If you have a hose with a nozzle on it and you grab the hose and try to squeeze it, it's really difficult to squeeze it. That's because of all the pressure pushing on the walls of the hose, right? But if you grab the water coming out the end of the hose and try to squeeze it, you squeeze your hand right through it. It's just like squeezing through air because it's the same pressure as the air, right? So we actually take advantage of this in many things that we use in in our everyday lives. You have the perfume, what they call atomizer. Have you ever used an atomizer? Not many people do these days. Have either of you used an atomizer for your cologne or anything? I actually have atomizers in the second semester of this class. We actually measure the mass to charge ratio of an electron. And the way that you do that is you have to get very, very small droplets of oil suspended in an electric field. And it's the only way to get a really, really tiny drop of oil is to use an atomizer. And the atomizer is like the perfume bottle you see with the little thing on it. It's an atomizer. That little bulb never has anything but air in it, by the way. All it does is squeeze air across the top of the perfume bottle. And the perfume bottle has a little pipe in it, and as air goes super fast across the top of the pipe, it creates a really low pressure region because of the fast moving air. That low pressure region is much lower pressure than the pressure inside the perfume bottle. And the pressure inside the perfume bottle pushes the perfume up to the top, and those little droplets of perfume get caught in that really fast moving air, and it comes out. And the reason for that is because the reason they use these with perfume is because most perfume is quite expensive. I don't know if you've ever bought perfume for a woman, or if you've bought perfume for yourself, or if you've bought very expensive cologne for a man, but it's pricey. Like really good perfume that's made from natural ingredients, it's hundreds of dollars per ounce, and usually you buy a small fraction of an ounce for $50 or $75, right? And you only want a tiny bit coming out at a time because it's extremely expensive and it's very strong, right? It's very strong odor. So you use the atomizer to do that. Another one that you're probably more used to is the idea of a fireplace. With a fireplace, you build a fire at the bottom. In this case, they're using natural gas at the bottom. And then you have air intakes. Now, some fireplaces actually have a separate air intake, but most of them just have a big a big opening in front so the air can come in the top and or in front and whatever. But what's happening here is that as you burn your wood or your gas or whatever you're burning, your pellets down here, the hotter air is rising up this chimney and it's drawing air in with it. It's going to draw in more air in with it, right? And that actually helps the air to travel up the chimney. You have the same thing with like a water heater. A water heater, you have hot air in the boiler that's coming up the middle of the water heater, and on the top you have this little chimney, and it draws in cooler air as well. And the cooler air does a couple of different things. It prevents this hot air also has gas in it, gases that are poisonous. This cool air that's coming in around the side prevents the hot air from getting into wherever your hot water heater is. So in your basement or wherever it is. So it prevents that from getting into your house, and it draws that up the chimney. You can also use this to prevent. So, for example, if you've got water going down a sink, there's this U-bend under the sink. It's also in a toilet. It's also under a shower. But the U-bend always wants to have water in it because the U-bend prevents gas from coming back up the tube. Because if you had sewer gas coming up the tube, your house would smell terrible all the time, right? But if you flush your toilet or something, it can actually pull that water out of the U-bend just by using a little vacuum. It just kind of pulls it along, and it can empty your U-bend, and then your house would stink all the time. And it does happen in houses every once in a while. If you put a lot of water down through a tube, and it sucks that out. Well, you can prevent that from happening by actually having a little air vent next to things like sinks and toilets and showers that draws air in. That will prevent that suction from happening. And so your house has vents all over it. If you look at the top of your house, you just have these little pipes coming up. You don't have any covers on them. Just little pipes every once in a while. Usually they're about 2 to 4 inches in diameter. Just coming out of your house. And that's just a vent. It's just an air vent that draws air every time water goes down through your sewer. It draws air in so that it doesn't pull the water through every time you flush, air wants to flow, and it pulls it through the vent instead of through the U-bend, so you don't lose your U-bend water. Also, this also explains how we fly with an airplane. Here's a wing. You've got flow of air coming in from the left here, and it's got 2 paths it can take. It can take this straight path down here, and it can take this longer path here. But regardless of the path it takes, the air has to meet up with itself here and here. So the air that's here and the air that's here is the same air that was next to each other over here. That's a requirement of laminar flow. Laminar flow says this air has to get here at the same time as this air does. So it doesn't slow down. So it doesn't create turbulence, is a better way to say that. So what happens is as it goes under the wing on this flat part, it just travels straight and it keeps going the same speed. But as it goes around the wing on the top, it has to speed up to catch up to it. And so the air on the top is going faster than the air on the bottom. Faster speed, lower pressure. Slower speed, higher pressure. High pressure, low pressure, that means the wing is going to go up. And that's how airplanes fly. Airplanes fly by moving forward, by creating this fast air over the wing so that it's fast enough so that this difference in pressure is big enough that it will lift the wing up. That's one of the things that makes an airplane go up. There's another thing called thrust as well that helps it go up. But Bernoulli's principle explains a fair amount of why airplanes fly. It's also how sailboats work. With a sailboat, you have this air that travels towards the sail, and as it travels towards the sail and goes around the back of the sail, it actually has a shorter distance to go than if it goes around the front of the sail. So the back of the sail is going to have a higher pressure than the front of the sail, and you're going to have air. You're going to have the force pushing on the back end of the sail. right? The way that you make the boat go forward is you turn the tiller in that direction, in whatever direction you want. So it only uses the force vector that is pointing in that direction. So here is the way that they actually measure the speed of a plane. They use a manometer. So we've actually used manometers before. It's a closed. One end is closed, this end is closed, and this end is open, so that air can come in this one and push on this fluid in the manometer. It's usually built like this, so that the open one is in the middle of the closed one. Essentially, the faster you go, the more this air coming in is going to push on this water, and the lower it's going to go here, and the higher it's going to go here. And that's how they can measure how fast they're going. However, the problem is what if the wind is blowing in the same direction that they're going? If the wind is blowing in the same direction that they're going, then this is going to measure them going faster than they're actually going. If the wind is blowing in the same direction that they're moving, then it's going to show them going slower than they're actually going. So they build another one of these things and they point the tube straight down. And by pointing the tube straight down, the wind going past it creates a low pressure or a high pressure effect. Essentially, it creates a low pressure effect all the time. But by comparing the two, they can actually determine how fast the wind is blowing. So it's then they can calculate how fast the plane is actually moving. If you ever take ground school to become a pilot, they will teach you that. I know because I took ground school. And then we have Torricelli's theorem. In Torricelli's theorem, you essentially solve this equation for the final velocity of something if it passes through a height change of height 1 to height 2, right there. And the pressure is not very different. If the pressure is pretty much the same in the beginning and the end, then it just cancels out. And Torricelli's theorem is for calculating the speed of a fluid when it goes down from one height to another height, essentially. So if you want to know how fast water is coming out at the bottom of a dam like this, Torricelli's theorem is a good theorem for that. Pressure is essentially the same here and here, but the height is very different and the speeds are very different. And this is what you're going to use in your experiment tomorrow. We're going to make an experiment very much like this. Instead of a dam and a lake and water coming out, we're going to use a bottle with a hole in the bottom and water coming out. So you'll have this. And the really interesting thing is for lakes, like for a big lake like this, the velocity of the top of the lake, so the velocity is how fast is it moving down as water comes out here. It doesn't matter how much water is coming at the bottom of a dam. The lake is not going to be moving very fast. It's going to be moving super slow. This V is essentially going to be 0. So this equation up here becomes V squared equals 2GH for most lakes because this number is so small it doesn't even matter. Right? It's like inches per day kind of speed for most lakes like that. But it also works for like the truck here where you're going from low to high. It works as well. As long as the pressure is about the same. So here we're going to actually do this. Let's see. Oh, actually, they're not going to use Torricelli's theorem here. They're going to use Bernoulli's theorem here still. So Bernoulli's theorem, they're going to use Bernoulli's theorem because we're going to solve for a beginning and ending pressure. We have a beginning pressure, 1.6 times 10 to the 6, and an end. It's going to go up the ladder 10 meters. So we're going to have a height difference. We'll start with a height of 0 and go up 10 meters up the ladder, and then we have a flow of 40 liters per second. So this 40 liters per second, we can use that to calculate the velocity of the water at the beginning by using the flow equation right here. Calculate that. Actually, that's the velocity of 1, and then they find velocity 2 at the end as well because it has to be the same flow at the end. So they're using everything we've learned so far this chapters, and then we plug those two velocities in with the initial pressure and the height difference, and we get the final pressure 2. And that's, they use everything here, the whole thing, and you can't even see the answer. That's kind of weird. And then you can even talk about power in fluid flow, because the power of something is equal to the energy divided by the time, right? You have energy per time, that's your power. Well, this is not quite energy. This is actually kind of like energy divided by volume. So it turns out that if you multiply this by flow, which is volume per time, you'll get power. So if you multiply Bernoulli's thing by Q, you get power. And power will tell you how much energy you can get out of this per second, essentially. So for a fire hose, that's got this this diameter and this pressure coming out, and we want to know what power does the pump have to supply the water. So this is really useful if you're trying to provide this amount of water to the firefighter up on the top. You have to know what kind of pump you need to use at the bottom, right? What size pump, what power that pump should be able to crank out, which is going to be equal to the pressure times the flow, or this entire, it could be this entire equation times the flow, but we're going to use to do the pressure times the flow, since we know the pressure that he needs. So the pressure is the 0.920 times 10 to the 6 and newtons per meter squared, and then we multiply by the flow of 40 times 10 to the minus 3 meters cubed per second, and we get a 36.8 kilowatts of power needed. So you need a 40 kilowatt pump or a 50 kilowatt pump maybe. So here's Purseu's law. So viscosity and turbulence. Viscosity is like, it's kind of like the resistance, it's kind of like the goopiness of a fluid. So fluids that are more goopy, it's a very technical term, kind of like, here they compare juice and syrup, where juice, if you pour juice through your fingers, it kind of flows through, it doesn't leave much on your fingers, but if you pour syrup through, and it kind of goops through and leaves a lot on your fingers, right? So things that have low viscosity tend to have less friction involved in their systems. Things that have higher viscosity tend to have more friction involved in the system, and friction leads to turbulence. So here's smoke rising through air, right? And it turns out that smoke has a fair amount of viscosity in air, and it becomes rapidly turbulent. You can see the first sign of turbulence right there, that little line, and then you can see more and more and more, and very turbulent. And it turns out that because of viscosity and turbulence and friction, you get, when you have a fluid flowing, you get layers of fluid flowing. And sometimes these layers are defined by different stuff in the fluid. For example, in the ocean, there's different layers of salt levels. So the top of the ocean has a different amount of salt in it than the bottom of the ocean and other layers in between. But then there's also layers of temperature. So different fluids will have different temperatures, and that will sometimes create these layers. And these layers will often have different velocities as they flow. And also the friction, at the bottom of the ocean, you have the friction with the bottom of the ocean. Whereas in the middle of the ocean, you don't have that friction with the bottom of the ocean. You just have friction between the layers. And at the top of the ocean, you have just one layer to have friction with, and the air friction with the air, which is very low. Friction on the bottom can be very, very, very high because of things sticking up, and the sand is very, lots of friction with sand and water. So then you can get lots of turbulence there, creating more and more issues. So it ends up being kind of this array of velocities in real life. If you want to know the frictional force, or the force caused by the viscosity of a fluid, then you have to go into this guy I can't even, Poiseuille's law. That's kind of how you pronounce that. My wife could probably do it better. She speaks French. But this involves a whole bunch of stuff. You got this coefficient of viscosity, so that's how goopy it is. And then you have the velocity of the fluid, and then you have the area that the fluid is in contact with the, oh no, is that the cross section? No, it's the area of the fluid in contact with whatever it's in contact with. And then you also have this length, which is actually the kind of like the diameter of the fluid or the height of the fluid or whatever. And then you can rearrange that to solve for the viscosity and actually, calculate the viscosity of the different fluids. In the end, what happens is that you get this law here, this Poiseuille's law, where you have a difference in pressure divided by this thing R, which is the resistance. And the resistance, again, is dependent on this viscosity, but this time it's 8 times the viscosity times the length that it travels through, divided by pi r radius. Our radius is the kind of like the radius of the pipe it's going through, whatever. And this is all very approximate. And what happens is, as you have fluids that are not very viscous, you get very laminar flow across the entire fluid, and fluids that are quite viscous, it becomes laminar flow, but more laminar towards the center than it is towards the edges. You get more of this kind of shortening of the flow here. And the difference is like this. This one has very laminar flow, and this one has very viscous flow. Very non-viscous is the first one, very viscous flow is the second one. So you may want it to be one way or the other. If you want a really, really tight flame, for example, or a tight whatever, then maybe you want a more viscosity. But if you want this long, straight flame, then maybe you want less viscous. And you can actually calculate the flow rate for viscosity here. Got that as well. And here they actually do that. They calculate the flow rate for a particular flow of blood. And you have to have the 2 different pressures that it's going to flow between. You have to have the radius of the artery or vein or whatever. Then you need to know the viscosity of blood and how long it's going to flow. Is it going to go from the heart to the feet? Is it going to go from the heart to the lungs? Whatever, you need to know that length it's going to travel, and then you can calculate the flow for that particular path. And it gets quite a bit more complex. Turns out that if you want to apply this in real life, like we're just looking at real life with this one, just kind of peeking at it. But if you want to calculate this in real life, it becomes an extremely complex equation. There's just so many factors involved. So we don't do that. Here you can see we have this is actually a kind of a continuity law for Poiseuille's viscosity issues here, where it's Q1 over R1 to the 4th and Q2 over R2 to the 4th now. Whereas before it was just Q over area or whatever when it was done. Now it's R to the 4th. A little bit more involved. So here we have a bunch of viscosities of different fluids. You can see air has fairly low viscosity. Other fluids have higher viscosity. Liquids much higher than gases for the most part. You have things like honey, it's 2,000 to 10,000, right? Maple syrup, 2,000 to 3,000. I tell you what, that maple syrup that's at 3,000, so good. It's the dark, they call it the dark grade syrup, and it's usually not sold in stores. What they sell in stores is usually the amber grade syrup. The dark grade is usually too strong for most people. It has super strong maple syrup flavor, and you can even taste a little bit of the wood alcohol in it. It smells a little bit like alcohol when you open it. But you can buy it on the maple syrup farms in the Northeast. My dad used to go to Vermont all the time for his job, and he'd come back with just this metal can, looked like a gas can, with maple syrup on it. You just stop at a farm and ask them, and they just go out there and open up their tap and give them this dark grade amber syrup. And, oh, so good, so good. Sit home and make waffles and have maple syrup. So, remember that when you have flow that splits into parts, you have one pipe here and you have 5 pipes here. You have to put an n in the continuity equation. So this is like one pipe that's 5 times as big as these pipes. So if this pipe is 1 meter across, if you have 5 of them, you don't use a radius of 1 meter. You use radius of 5 meters, or you multiply it by 5. You can either do it, but you have to account for that. We did that in one of the examples before. You have to do that, and that's one I think in the homework. So you have to be aware of that. Okay, so when does turbulence start? This is going to be Reynolds' law and Reynolds' number, and this is the equation. The Reynolds number, N sub r, is equal to 2 times rho times V times R over viscosity. So rho is the density, V is the speed of the flow, and R is the radius of the tube. 2 is just 2. Divided by the viscosity, that gives you this number, Reynolds number. When Reynolds number is about 2,000 or below, then you have good laminar flow for the most part. If it's 3,000 or above, it's usually pretty turbulent. If it's in between 2,000, 3,000, it's iffy. So that's a simple thing. You just kind of plug in numbers and calculate. So here they want to calculate the Reynolds number for the flow in the needle considered in example 12.8. Verify the assumption of flow is laminar. Assume the density of saline solution is 1025 kilograms per meter squared. I don't remember what this is. Oh, right. This is when they were putting the saline solution in the patient. And we didn't actually talk about it. We just kind of talked about the equation they were using. But when they're putting saline solution in the patient, that saline solution has a viscosity. It has a length of the tube that it has to go through. There has a radius of the tube or the needle that it has to go through, and there's a change in pressure from the height of the IV bag, right? And then you can calculate the flow going into that. In our case, in our case, we want to know when you get turbulent flow in that thing, because at some point you're going to get turbulent flow, and that will impede the movement of the fluid through the bag. So the density of the saline solution they give to us, we actually know, let's see, what do we know we know rho, that's what they just gave to us. We know the velocity from the previous problem, which they actually give to us here. Then we know the R of the needle, radius of the needle, and we know the viscosity of the needle, which is the viscosity of water, essentially. So they put all that in there. We get a N equals 523, which is definitely below 2,000, so it's going to be laminar flow. Simple. Plug and chug, as we used to call it. So, you can also calculate the Reynolds number for an object in a fluid that's moving through a fluid. And in that case, it's rho times the velocity of the object, rho of the fluid times the velocity of the object, times what is called the characteristic length of the object. And that's actually kind of how big the object is facing the direction it's going in the fluid. So if they do this, the Reynolds number for a ball going through air at 40 meters per second, right? So you have the density of air, which is 1.29 kilograms per meter cubed. You have the speed of the ball, 40 meters per second. And then you have the length of the ball, which is essentially going to be like the diameter of the ball, right? Divide that by the viscosity of air right there, and you get 2.11 times 10 to the fifth. Now this is very high, so it could easily be turbulent. It definitely we would consider this turbulent. And is turbulence a factor throwing a baseball? The answer is yes. That's what makes baseballs curve, is turbulence. And also Bernoulli's law. As you throw a curveball, you're actually going to throw the ball in such a way that it's spinning really, really fast, kind of sideways, right? Kind of at an angle. And when it's spinning really, really fast, the speed of the air on one side of the ball is much, much faster than the speed of the air on the other side of the ball. Most curveball throwers throw the curveball like this on the outside. Most are right-handed. They're throwing it like this on the outside. That means that the top of the ball is experiencing a much faster air than the bottom of the ball. Where's the pressure going to be higher? Fast-moving air or slow-moving air? Slow-moving air. So the pressure is higher on the bottom corner of the ball. And what does a curveball do when you pitch it? You pitch it down like this, and it goes up. Because the pressure is high bottom of the ball, right? Then, as turbulence kicks in, it slows the ball down. So slows the spinning down because turbulence kicks in because the threads of the ball create turbulence and the ball's moving really fast. So you get turbulent flow, so it starts to slow down that spin, and as that spin slows down, that pressure is no longer pushing that ball out there. So what happens to it? It comes back in to where it was originally going, and you get this curve on the ball. Right? What happens with a knuckleball? What's a knuckleball? Knuckleball is where they throw the ball without any spin, right? So they throw it, has no spin. Really good knuckleball throwers can throw the ball fast with no spin. So it gets a lot of turbulence. Well, the turbulence in that case is random. It's wherever you line up the seams on the ball, and it's going to be behind the ball for sure, and it's going to be in front of the ball for sure. You can have random turbulence. So what happens to a knuckleball? It moves around a lot. In fact, a fastball moves around a lot too, because it still has turbulence. It doesn't move as much in the time that it's in the air because it goes so much faster. It's in the air so much less time between pitcher and plate, so you don't see the movement as much on a fastball. On a really, really hard fastball, you won't see the movement at all. A lot of people say, well, people that throw the ball too fast have no movement on the ball. It's not true. The faster you throw a fastball, the more movement you have on the ball, no matter what. But you see less of it because it moves so quickly from pitcher mound to plate. Yeah. So why is it that it's sometimes harder to hit a softball than a baseball? Softballs are thrown much slower than baseballs. Why is it that it's sometimes harder to hit the softball? Because they pitch it from 10 feet closer in. Actually, I think it's more than that. I think it's more like 50. So it's 60 feet 6 inches, and I think it's 46 feet or 48 feet for something like that. So it's a lot closer in. So you don't even have time to see the ball move with a softball some of the time. And they have very different spin on the ball too. A fast pitch softball is very difficult to hit. A slow pitch softball, of course, anybody can hit. It's pretty much guaranteed you're going to hit. But unless you don't watch the ball. They once had a guy pitch in slow pitch softball. He was just practicing out in the field, and I felt like swinging the bat, so I went out and said, "Oh, I'll hit balls while you're pitching this." He said, "Okay." I hit every ball he pitched for like a half an hour, and he's like, "Man, that's amazing." I'm like, "It's really not. Slow pitch softball is not hard to hit. Try a fast pitch softball. That's hard to hit. Try a fast pitch fastball, a fast pitch hardball. That's hard to hit." Slow pitch softball is just like not hard. Anyway, so here they calculate the turbulence of baseball. Look at that turbulence. That's a thing of beauty. There's a curveball for you. There's a book called, it's actually a textbook called The Physics of Baseball. There's your knuckleball right there. One version of a knuckleball. So here's what you see normally when somebody's pitching, right? Arm here, this very open stance. That's not what I'm looking for. There it is. That is not what you normally see. And that doesn't even really show what I'm looking for. When he's in his full stance, this is what he looks like. So this guy, what is his name? I can't remember all of a sudden. Tim Lincecum. Tim Lincecum won the Cy Young Award 2 years in a row, I think. And he's like 5'8", 5'9". He weighs like 140 pounds, 138 pounds or something like that. And he's like totally geek, nerdy kind of guy. But he just went to his dad after watching a baseball game once and said, "Dad, I want you to teach me how to play baseball. Teach me how to pitch a baseball." And his dad's an engineer. His dad didn't know anything about baseball. So he went and read up on the physics of it and watched a bunch of pitchers pitch. And he taught his boy how to play baseball in a very different way. And he'd pitch a baseball in a very different way. And he's pitched one of the fastest balls ever recorded, like 104 miles an hour or something like this. And you have, people like the Freight Train and the whatever else, and all these guys that are like 6'7" and like longer than they've got these huge arms. This tiny little guy comes out there and blows them all away because it's physics. And he threw the ball in such a different way. He learned to wind up so that his arm comes almost all the way behind him and down past his thigh here when he winds up, so that he gets all of that rotation and all of that whip of the ball, essentially all that torque on the ball. It's a huge amount of torque on the ball for such a small pitcher, and he has a very different pitching style than others. Won a couple of World Series, and all for my team, the San Francisco Giants. Okay, back to physics. Anyway, the last section is molecular transport diffusion. So this, I'm not going to really test you on any of this stuff. This is a way of calculating the what we call the root mean squared of distance that something travels when it travels in a random pathway. But this is actually how things like diffusion happen when you have, and diffusion is responsible for things like osmosis and stuff like that. So in biology, the way things work, the way things move, in this, for example, they're talking about a sugar moving 1 centimeter in just water. So if you put sugar in water, how long does it take for the sugar to move through the water? Which it does. It's very, very slow, in fact. But those processes can be changed because of the minute things that are happening, the heat that's going on, other things. So when something is going from inside of a cell to outside or outside the inside, if you want to get sugar into a cell, for example, or ATP or salt or whatever else, in and out of a cell, it's moving through a liquid and it's moving randomly, and it has to move through these tiny little holes randomly. Everything is random. It's kind of crazy, but physics explains it all. Physics describes it all. And it's something that was not well known and not well studied until recently, actually, because it took so much math and so much computer power to kind of model it and make it and to prove that it was correct. Really. But it's quite interesting. And so this has given birth to a whole new, so a lot of, for example, kidney patients, people who have kidney disease, kidney failure, have to go through a process called, they talk about it here somewhere, dialysis right here. So dialysis, where they pump all the blood out of their body and put it through this machine that cleans the blood, essentially, because the kidneys are like the filters for your blood. And this machine this machine is designed to do this using these physics techniques, these physics ideas. Before they started understanding the physics of it really well, these machines were huge and they worked terribly. Then they started understanding the physics and they were able to design them better because they understood what they were supposed to do and how they were supposed to do it. And now they're quite small and quite efficient, and kidney patients can now live a very long time without kidneys, without working kidneys, while they're waiting for a transplant, which is really important. For people that are waiting for a kidney can be very sick and have a very, very poor life. But if they can still be alive, that's good, because kidney patients before this just had a few weeks on these things, maybe a few months. But I had a friend that was on dialysis for, I think, a couple of years. Eventually, she had to have a kidney transplant because eventually it just gets so bad. But they had a problem finding a match for her, a kidney match. Eventually, it turns out her husband was a perfect match. And now they share kidneys. Anyway, that's all we have for you for chapter 12. So go ahead and get started on the homework. A little more calculation in this homework, but still, the level of difficulty is not really all that high compared to what we've done so far in this class. Tomorrow we'll answer questions really at the beginning of class for homework, so get that done quickly. Also, my TA will be here before class if you want to come in and get some help. I know that a couple of you have. He's more than happy to do that. And then we'll do a lab after we're done with homework. So we'll see you later.